All right, let's jump right in with a classic physics puzzle. Now, this seems really simple on the surface, but the answer, it tells us something fundamental about how pretty much everything moves, from a simple baseball all the way up to a satellite orbiting the Earth.
Okay, so picture this in your head. We've got two baseballs. One we just drop straight down. At the exact same instant, from the exact same height, we shoot the other one out completely horizontally. Now, your gut is probably screaming that the one that was fired has to travel way farther, right? So it must land later, right? And there it is. In a world without any air getting in the way, they smack the ground at the very same moment. I know, that feels completely wrong, but physics can be super counterintuitive sometimes, and by the end of this, you'll see exactly why this happens.
To solve this mystery, we can't look at the whole thing at once. We've got to break it down. And our first big clue comes from looking at just one direction, up and down. Let's just focus on the vertical motion for a second.
You know, if we could watch this in super slow motion and take a little snapshot every fraction of a second, we'd see something amazing. At every single moment, a tenth of a second in, 2/10, 3/10, the two balls are perfectly lined up with each other vertically. They are falling at the exact same rate, lockstep.
And that's the first huge piece of the puzzle. The fact that one ball is zooming forward has absolutely zero effect on how it's moving downwards. As far as gravity is concerned, it's behaving exactly like the ball that was just dropped. They are both just falling.
So what's the force dictating that fall? It's this number. This is what physicists call g, the acceleration due to gravity here on Earth. And it's a constant. It pulls on both baseballs exactly the same, making their downward speed pick up at the exact same rate, no matter what they're doing sideways.
Okay, so we've cracked the vertical part of the motion. They fall together. Got it. Now for clue number 2, let's completely switch gears and only look at the horizontal forward movement of that fired baseball. Remember those slow-mo snapshots? Well, if we measure how much ground the fired ball covers between each little flash of the camera, we find something else that's really cool. The spacing is perfectly even. It travels the same horizontal distance in every single tick of the clock.
And what does that tell us? It means the ball isn't speeding up or slowing down in the forward direction. Once it leaves the barrel, it just coasts. There are no forces pushing or pulling it sideways, so its forward speed just stays the same, all the way to the end.
So now we have our two big clues, right? We have a constant downward acceleration, thanks to gravity, and we have a constant forward speed. So how do these two completely separate things combine to solve our puzzle? Well, let's put them together.
This table, right here, shows the secret sauce of projectile motion. The vertical and the horizontal worlds are completely independent. You can think of them as two separate movies playing at the same time. Gravity owns the vertical y-axis, making things speed up. But on the horizontal x-axis, it's just smooth sailing, no acceleration at all.
And that beautiful, elegant curve, that parabola you see every time you throw a ball, it isn't one complicated motion. It's actually the simple sum of two much simpler motions, coasting forward at a steady speed while at the very same time falling faster and faster and faster towards the ground. Okay, that explains a ball shot perfectly horizontally. But what about a more realistic throw? You know, like a baseball getting hit by a bat or a soccer ball getting kicked. It starts by going up and forward at an angle. Do the same rules still apply? You bet they do.
So here's the trick. You take that initial launch speed, the one that's at an angle, and you just break it down into two separate pieces. We call this resolving it into its components. You figure out how much of that speed is purely horizontal and how much is purely vertical. And then you just analyze them separately using the exact same rules we just talked about.
So what happens in the air? Well, that horizontal part just keeps chugging along, same speed the whole way. But the vertical part, it's in a constant battle with gravity. It starts by going up, so gravity slows it down, brings it to a complete stop at the very top of its arc, and then starts pulling it back down, speeding it up again until it lands.
And this leads us to the official definition. Any object that you throw or shoot or launch into the air and then moves only under the influence of gravity, that's a projectile. This doesn't count something like a rocket, which has its own engine pushing it. A projectile is in what we call free fall the moment it leaves your hand or the launcher.
So what's the big takeaway here? The real secret to understanding the path of any thrown object is to stop seeing it as one complex curved line. Instead, just break it down into two simple, independent motions, a constant forward coast and a constant downward acceleration. Analyze them separately, and you can figure out any projectile problem.
And that just leaves us with one final thought to chew on. You now have the tools to analyze any throw. But think about this. Gravity on the moon is only about 1/6 as strong as it is here on Earth. So if an astronaut hit a golf ball up there, how would that change our equations? How much farther would that ball really fly? Something to think about. Thanks for tuning in.